Today's topic is the logic of hypothesis testing. This is our transition from descriptive statistics to inferential statistics. Inferential statistics are the procedures where we have information about samples and we use them to determine something about a population. So instead of measuring the whole population, like every person in the world, we're going to measure a sample and assume that that sample represents a population. There are several types of inferential statistics. We will be focusing heavily on hypothesis testing because it's still the most prevalent method used in psychology. With hypothesis testing, we start with a measured or an observed sample. And we'll be asking if this sample is typical of the general population. If the sample mean is one that commonly occurs, then we determine that it could just be a random sample pulled from the general population. As a result, our sample data are considered inconclusive. We can't determine much about the population from this sample. On the other hand, the sample we measure could be very unlikely to have come at random from the general population. In this case, we'll conclude that the sample is probably not from the general population. Instead, it's probably from a different population, a population that has a specific feature or a specific trait of interest. So the logic behind hypothesis testing hinges on whether a sample is likely or unlikely to come from a population at random. Let's get into an example to show how we will determine whether a sample mean is likely or unlikely to have occurred by chance. In this example, we have a researcher who is interested in studying aggression. She has a hypothesis that watching television increases aggression. She knows some things about the population. She knows that the population mean is 2 and that the population standard deviation for aggression is 1. So in this case, she knows mu and she knows sigma. This researcher studies a sample of 30 children who watch 10 hours of television per week. In this case, 30 is her sample size. And the thing that makes her sample unique, the thing that represents her hypothesis, is that these are kids that watch a lot of television. We're going to walk through a 4-step system to test this hypothesis of hers using this sample. Step 1 is to state your hypotheses. We are going to state our hypotheses verbally as well as mathematically. And we will describe 2 different hypotheses, one that the researcher's idea is true and one that the researcher's idea is false. All in all, this gives us 4 hypotheses. Let's start with the easiest of the hypotheses. This is the verbal research hypothesis, which is sometimes called the alternative hypothesis. This is a statement that the researcher's idea is true. In this case, the verbal research hypothesis would be that watching television increases aggression. The verbal null hypothesis is a statement that the research hypothesis is false. So in this case, the verbal null hypothesis would be that watching television does not increase aggression. Next, we will write out our mathematical hypotheses. These hypotheses are going to be about the population our sample might represent, so we will use mu in writing them. Our mathematical research hypothesis will be labeled as H1, and it will read that mu, or the population of kids who watch a lot of television, will have a mean greater than the regular population, which we already know to be 2. So this hypothesis sets up what we expect our sample's population to be relative to the general population. Our mathematical null hypothesis will show that the opposite of our research hypothesis, in this case, that mu should be less than or equal to 2. In this way, the null and alternative hypotheses combined cover every possible basis if our sample's population mean is less than, equal to, or greater than 2. Remember, we're hypothesizing about populations, and so we're going to be using population symbols. Okay, now we're ready to move on to step 2. In this step, we're going to establish the criteria for deciding whether the null hypothesis is likely true or likely false. The first part of this step is describing the sampling distribution of the mean. This sampling distribution is going to represent what would happen if you pulled every possible sample of your sample's size from the population. We need to describe the sampling distribution in terms of the 3 criteria we always use: its shape, its standard error, and its mean. In the example we're working with, we know the population mean and the population standard deviation. And so it turns out that this example is actually what is called a z-test. We'll cover that formally soon. Because our sample is over 30, we know that its shape is normal. The mean of the curve can also be known because we know that the mean of the sampling distribution of the mean equals the population mean. So in this case, mu sub x bar equals 2. Finally, we can know the standard error, or the standard deviation of our distribution, because we know n equals 30, and we know that the standard deviation of the population is equal to 1. The second half of step 2 is labeling our critical region. This is also called the rejection region. This is where we set up the cases that we would consider unlikely to have occurred by chance if the null hypothesis is true. The rarest sample means in our sampling distribution are in the tails. These are the sample means least likely to occur by chance. At this point, we need to decide whether our test is a one-tailed or a two-tailed test. When the research hypothesis includes a specific direction, it is a directional hypothesis, and that means it's one-tailed. Our example is one-tailed because we expected a specific direction of watching TV, an increase in aggression. In this case, then, we have one rejection region. We place this rejection region in the place least likely to occur if the null hypothesis is true. Here, that region is on the right. If the null hypothesis is true, then we would not expect the sample mean of kids who watch a lot of TV to be large. The other thing we need to do to determine our rejection region is to know our alpha, or the probability of what we consider rare. In psychology, that's usually 0.05. That is, we say rare cases should happen 5% or less of the time. Knowing the alpha and the tails will set your critical value. This critical value is the line at the boundary of the critical region. Remember, that's also called the rejection region. That's all we need in order to set up our criteria, the sampling distribution and then the rejection region with the labeled boundary. In step 3, you'll compare your sample mean to the mean that you expect by chance. We'll talk about specific formulas for step 3 as we learn each new statistical test. Step 3 was so easy. Step 4 is actually pretty easy too. So in this step, you're going to compare your obtained statistic from step 3 to your critical statistic from step 2. First thing we do is make a quick and dirty decision about the null hypothesis. Do we retain the null hypothesis or do we reject it? If the obtained statistic falls in your rejection region, then it will be larger than your critical statistic and you will reject the null hypothesis. Note that if you're working with a one-tailed test, you'll have to make sure it's not just the absolute value that's larger, but that the obtained statistic actually falls beyond the critical statistic on the sampling distribution. If the obtained statistic does not surpass your critical statistic, then you'll retain the null hypothesis. To wrap the whole 4-step system up, you make a verbal conclusion about the research hypothesis. This was the idea that got you started in the first place. You'll either conclude that you have or do not have evidence for your research hypothesis. If you reject the null, then you get to say that you have evidence for the research hypothesis. In our specific example, we would say there is evidence to suggest that watching television increases aggression. On the other hand, if you retain the null hypothesis, then you have to say you don't have enough evidence for the null. In our example, you would say there is not evidence to suggest that watching television increases aggression. Note that we never say the word prove. Because we're talking about probability, we simply talk about evidence for or against our idea. Is our idea likely or unlikely? Because we are working with probability, we're also sometimes going to make conclusions that are wrong. Type 1 errors are when we reject the null hypothesis even though it is true. That is, we decide our sample mean looks rare and it's unlikely to have occurred by chance. But because we use probability, these mistakes are bound to happen sometimes. In fact, the rate of making a type 1 error is exactly equal to our alpha rate. That is, about 5% of the time, we make a type 1 error, rejecting the null hypothesis when instead we should have retained it. Type 2 errors happen when we retain the null, even when it's false. That is, we decide we don't have evidence for our research hypothesis, but our idea is actually correct. We're pretty flexible with our type 2 error rates. In psychology, we try to make sure that when we retain the null, we are only doing so erroneously about 20% of the time. Type 1 and type 2 errors happen when the results from our sample don't match what we would observe if we studied the whole world. That is, if we actually knew reality. If our sample says to reject the null hypothesis, but in reality the null is true, that's when we make a type 1 error. If our sample says to retain the null hypothesis, but in reality the null is false, that's when we could make a type 2 error. Type 1 error rates, like I said, are always set by our alpha, but we can actually change our type 2 error rates in a lot of ways. We do this by trying to increase our statistical power. Statistical power means we increase our chances of rejecting our null hypothesis based on our sample, when in reality, the null hypothesis is false. So we reject it when it's false, and it is false. We can increase statistical power in a lot of ways. So first, we can actually increase our sample size. When we make our sample size bigger, we make our sample look more like the population. Larger samples more strongly represent the population they come from. So our sample results will be more likely to match reality. Another way we can increase statistical power is by increasing our alpha rate. Unfortunately, if we increase our alpha rate, we also increase our type 1 error rate. So although this decreases type 2 errors, there's only so much we can budge on alpha. You'll be hard-pressed to go higher than an alpha of 0.05. A related way to increase power is to use one-tailed tests. These tests focus all of our alpha in one place, making our critical statistic smaller. And when that critical statistic is smaller, it's easier for the obtained statistic to surpass it. A final way we can increase our power is to use larger effects. If you're interested in, say, the effect of therapy on depression, you could measure its effectiveness after 3 sessions or after 15 sessions. You'll probably see a bigger difference due to therapy after more sessions. If our researcher wanted to increase her effect size, she could study only kids who watched 15 or 20 hours of television per week. This would give her more statistical power than observing kids who watch 10 hours of television per week.